Welcome to the Sleepy Scholar. It's good to have you here tonight. Wherever you are, whatever corner of the world you've folded yourself into, under a blanket, on a couch, on the last train home, with a lamp still glowing somewhere just out of reach, I'm glad you came. Settle in. There's nothing you need to do for the next little while except breathe. And let your shoulders come down from wherever they've been holding themselves all day. I want to ask you something before we begin, and you don't have to answer out loud. Where in the world are you listening from tonight? What time is it in your corner of the night? Somewhere it's late and raining. Somewhere the heating has just clicked off and the room is cooling by a degree. Somewhere the window is open and the air smells like cut grass, and somewhere else it smells like nothing at all, just the clean quiet of a house gone still. Hold that where you are in your mind for a moment. We'll come back to it at the very end. It matters more than you'd think. And if you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on it more than you'd guess. And to those of you already here, already part of the small circle of people who come back night after night, thank you. Genuinely, you're the reason the lamp stays on. Now here's the promise I'll make you tonight, and it's a gentle one. We are going to move slowly. We're going to take one enormous, strange, beautiful idea and turn it over in our hands like a smooth stone, one facet at a time, and there is no rush at all. You don't have to follow every step. You don't have to hold every number. If you drift off somewhere in the middle, if you never hear how it ends, that's not a failure. That's the whole point. The ideas will still be here, the sky will still be here, and so, honestly, will I. I'll try not to make this so interesting that it keeps you awake, but if it does, well, at least you'll have learnt something. A fair trade. So let me tell you what we're going to be thinking about, softly, as you fall asleep. Tonight, if you were to step outside, away from the streetlights, out to where the dark is really dark, and let your eyes adjust for 20 patient minutes, you'd start to see them. Stars first, thousands of them. And then, if you knew where to look, a few faint smudges among the stars, soft little patches of light that aren't stars at all, but entire other galaxies, each one holding 100 billion suns of its own. It's a staggering thing to look at. A sky full of other worlds. And here is the strange, quiet fact I want to give you tonight. The one we'll spend the whole of this journey unfolding. Almost every galaxy you can see out there, nearly all of them. The overwhelming majority of everything the great telescopes have ever photographed is already impossible to reach. Not difficult. Not far. Impossible. You could not get there if you left tonight. You could not get there if you left at the speed of light. You could not get there if your descendants spent 1 billion patient years chasing after it. The door to those places is already closed. And here's the part that makes my chest go quiet every time I sit with it. That door didn't close last year, or in some far future we have to worry about. It closed long before you were born. It closed before there were people to notice. Roughly 94% of the galaxies glittering in tonight's sky were already out of reach when the first human being looked up and wondered what they were. You can see them. You can never go. And you already couldn't. I know. Sit with that for a second. It sounds like a contradiction, doesn't it? How can something be sitting right there in your sky, its light literally landing on your eye, on the lens of a telescope, close enough to photograph, and yet be somewhere you could never, ever travel to? even in principle, even with all the time in the universe. That's the puzzle. That's the whole gentle mystery we're going to drift through tonight. And I promise you, by the end it won't feel like a contradiction anymore. It'll feel like something softer than that. Something almost tender. Because the truth is that there isn't one map of the cosmos. There are two. And they don't match. Let me explain what I mean, slowly. There's the map of everything we can see. Astronomers call it the observable universe. It's the sphere of space around us that light has had time to cross since the beginning, everything close enough that its glow has reached us by now. And you'd think, wouldn't you, that if the universe is about 13.8 billion years old, then the farthest we could possibly see would be about 13.8 billion light years, because that's how far light could have travelled in that time. It's a reasonable guess. It's also wrong, and the reason it's wrong is the first thread we're going to pull on tonight. The observable universe is much, much bigger than that. It stretches out to about 46.5 billion light-years in every direction. 46.5, not 13.8. Which means the whole sphere of what we can see is something like 93 billion light-years across. That's the width of the visible cosmos, corner to corner, one edge of what's seeable to the other, 93 billion light-years of galaxies. How can we see something 46 billion light-years away when the universe has only existed for 13 billion years? Hold on to that question. It's a beautiful one, and it has an answer, and we'll get there, unhurried, for now. Just hold the shape of it. The map of the visible is enormous. 46.5 billion light-years out in every direction. Write that number softly on one side of your mind. Now here's the other map. And this is where the ache comes in. There's a second boundary out there. It doesn't mark how far we can see. It marks how far we could ever go. Everything inside it is, at least in principle, reachable, a place we could send a signal to. A place a traveller leaving today could someday arrive, if they left right now and moved at the absolute limit, the speed of light itself. And everything outside that boundary is sealed away forever. No signal we send today will ever arrive. No traveller, however fast, however patient, will ever catch it. Astronomers call this second boundary the cosmological event horizon, and it sits at a radius of only about 16 billion light-years. 16, not 46. Do you feel the gap? On one side of your mind, the map of what we can see, 46.5 billion light-years. On the other side, the map of what we could ever reach, barely 16. The visible cosmos is almost 3 times wider than the reachable one, and because these are spheres, because volume grows with the cube of the radius, that difference isn't 3 times bigger, it's far, far more than that. When you do the arithmetic, the reachable region turns out to be only a small handful of percent of the visible one, somewhere in the neighbourhood of 3 to 6%, which is exactly where our number comes from. If only a few percent of what we can see is reachable, then more than 90% of it isn't. 94%. In the usual telling, 19 galaxies out of every 20, already, permanently, on the far side of the line. Now, I want to be honest with you, because honesty is part of how you fall asleep in peace and not in doubt. That exact figure, 94%, isn't a thing anyone measured with a ruler. It shifts a little depending on precisely how fast we think the universe is expanding and precisely how dark energy behaves, and those are things scientists are still arguing about, gently, in journals. So don't hold the 94 too tightly. Hold this, instead, because this part is rock solid, More than 9 out of every 10 galaxies you can see are already beyond any possible reach. The exact digit wobbles. The enormity of it doesn't. Most of the sky is a place we can only ever look at, never visit, never touch, never answer. And I'll show you, before we're done, exactly when that door closed for any given galaxy. There's even a number for it, a specific point past which a galaxy is already lost to anything we could send it. When we get there, you'll be able to look up at a smudge of light and know, more or less, whether it's on the near side of the line or already gone. But that's for later. No rush, let it wait. For now, just let the two maps sit side by side in the dark. The map of the seen, the map of the reachable, and the strange, quiet space between them, full of galaxies we will love forever from exactly this distance and no closer. I told you it wouldn't feel like a contradiction by the end. Here's the first hint of why. When you look up at one of those far galaxies, you're not really looking at a place you could go and simply haven't. You're looking at light, and light is a kind of history. The glow landing on your eye tonight left that galaxy long, long ago and travelled all this time to find you. And while it was travelling, the galaxy that sent it drifted further and further away, carried off by something we'll talk about in a while. So the thing you see and the place it is now are not the same thing at all. You see the letter. The sender has already moved somewhere you can't follow. In some cases, somewhere no letter of yours will ever reach. That's the ghost at the heart of tonight's story. We are, quite literally, watching light from places we've already lost. A galaxy can be sending us its glow, we can photograph it, study it, name it, and at the very same time be somewhere that a beam of light leaving Earth tonight could never, ever arrive. We keep receiving. We can no longer reply. It's a little like getting a postcard from someone in the mail, reading it by the light of your lamp, and slowly realizing that by the time it reached you, they'd already gone somewhere with no address at all. The postcard is real. The connection in the postcard is real. But it only runs one way now. And it always will. I'll unfold exactly how that works later, how something can send you light while being unreachable. It's one of the gentlest, saddest, most beautiful ideas in all of physics, and it deserves its own slow moment. Later, for now, just know the ghost is there, and we'll meet it properly. And there's another loophole waiting for us. One that sounds impossible until you see how it's allowed. These far galaxies aren't just drifting away slowly. Many of them are receding from us faster than the speed of light. Faster than light. And I can already feel some part of you, even half asleep, going, wait, isn't that against the rules? Didn't Einstein forbid exactly that? And the wonderful answer is no. Not this. Einstein is perfectly at peace with what these galaxies are doing. There's a loophole, a real and legal one, written into the very structure of how space behaves, and when I show it to you, it'll click into place so cleanly that you'll wonder why it ever seemed strange. But that, too, can wait. Let it be a small, warm coal of curiosity, banked for later. So here's everything I've promised you now. All the little doors will open on this slow walk. There's the 94%, the sheer scale of what's already lost. There's the loophole, how a galaxy can flee faster than light without breaking a single law. There's the ghost light, how we keep seeing places we can never reach. And there's a strange, lonely future I want to tell you about near the end, a night sky billions of years from now where someone looks up and sees only a single galaxy in an otherwise empty blackness and concludes, wrongly, but understandably that theirs is the whole of everything. All of that is coming. None of it is urgent. We'll take each one when we come to it, and not a moment before. But before we go out to the far edges, before we talk about billions of light years and horizons and the deep future, I want to bring the whole thing close, right down to what you could actually see with your own two eyes tonight. Because there's a small mercy hidden in all this, and I don't want you to fall asleep before you've heard it. Here it is. Yes, almost every galaxy in the sky is already out of reach. But not all of them. There's a small, precious handful that are not lost. A few galaxies that will stay reachable forever, that no expansion will ever carry away, that are bound to us by something stronger than the stretching of space. And here's the lovely part, the part that makes me smile every time. Those few reachable galaxies, the ones that are truly, permanently ours, are exactly the ones you can see with your naked eye. You don't need a telescope for the galaxies you could actually go to. You need a telescope for all the ones you've lost. The unreachable 94% are the faint ones, the ones that only show up on long exposures and deep sky surveys. The reachable few are bright enough to point at. Let me take you on that small tour, because it's a soft and comforting one. If you're in the northern half of the world tonight, and you find a properly dark sky, and you look toward the constellation Andromeda, you can see, with nothing but your own eyes, the Andromeda Galaxy. Astronomers call it M31. It's about 2.5 million light-years away, which makes it, remarkably, the most distant thing the human eye can see, without any help at all. Think about that for a moment as you lie there. The faintest little oval smudge, no brighter than a breath of fog on glass, and it's 2.5 million light-years off. And it's an entire galaxy, a trillion stars, and the light landing on your eye left it 2.5 million years ago, before your species wore its current shape. You can hold all of that in a single glance. It's the farthest your unaided eyes can ever reach out into the dark. And it is reachable. It's one of ours. Hold that. Then, if your sky is truly dark and your eyes are truly patient, you might catch a second one nearby, the Triangulum Galaxy, M33. It's fainter, harder, a real test of a good dark sky and good eyes. It sits about 2.7 to 3 million light-years away. It's a spiral, like our own Milky Way, seen almost face-on, and under the right conditions it reveals itself as the very faintest possible glow, right at the edge of what a human eye can do. Most people go their whole lives without knowingly seeing it. But it's there, and it too is one of the reachable few. And then, if you're in the southern half of the world tonight, Australia, or Chile, or South Africa, or a ship somewhere in the Southern Ocean, you have two companions the northern sky never shows, the large Magellanic Cloud and the small Magellanic Cloud. Two soft, luminous patches that look almost like torn-off pieces of the Milky Way itself, drifting in the dark. The large one is about 160,000 light-years away, the small one about 200,000. They're small galaxies, satellites really, circling our own like moths around a lamp. Early sailors used them to navigate the southern seas. And they, too, are ours to keep. Now here is the thread that ties this little tour to everything else. The thing I want you to carry down into sleep. Every single one of those naked-eye galaxies, Andromeda, Triangulum, both Magellanic Clouds, belongs to the same small neighborhood we do. Astronomers call it the local group. It's our cosmic hometown, the Milky Way and Andromeda and Triangulum and the Magellanic Clouds and around 80 smaller galaxies besides, all held together in a loose gravitational embrace. And because they're held together, because gravity has them by the hand, the expansion of space doesn't pull them away from us. Inside a bound group like this one, the stretching of the cosmos simply doesn't operate. These galaxies stay. They're not going anywhere. They're the ones that will still be reachable 100 billion years from now, long after everything else has slipped over the horizon and faded from view. So do you see the shape of the irony now, the one the whole night rests on? The galaxies you can literally point at with your finger tonight are the tiny, reachable minority, and the vast, glittering, uncountable majority, the ones filling every deep photograph the great telescopes have ever taken, those are the ones already gone. The closer something is, the more likely it's still ours. The farther and fainter, the more certainly it's lost. When you look up at the few soft smudges your eyes can find, you're looking at the whole of what we could ever visit. Everything beyond them is a view, and only ever a view. I find that strangely comforting, honestly, not sad. Or sad, yes, a little, in the way that a beautiful thing is sad. But mostly comforting, because it means the cosmos we can actually belong to isn't some incomprehensible 93 billion light-year abstraction. It's a neighborhood. It's small enough to have a name. It has a handful of members you can greet by eye from your own backyard. The unreachable universe is magnificent and vast, and it will break your heart if you let it. But the reachable universe is cozy. It's a group of houses on a quiet cosmic street, and the lights are on in all of them, and none of them are going anywhere. Let that settle over you like a second blanket. The sky is enormous, and most of it is already lost, and yet the part that's truly ours is close, and bright, and permanent. And you can find it with nothing but your own two eyes on a clear, dark night. Now, before you drift too far, let me plant one more seed for later, because it's going to matter, and I want it waiting for you when we come back to it. I said the observable universe stretches out to 46.5 billion light years, even though the universe is only 13.8 billion years old. And I asked you to hold that as a puzzle. Here's a little more of it, just enough to keep the fire warm. The reason we can see so much farther than light could simply have travelled is that space itself has been growing the whole time the light was in flight. A beam of light that set out toward us long ago has been, in a sense, carried further and further by the stretching of the very space it's crossing, like a swimmer trying to reach shore while the whole sea slowly widens beneath them. The light travels, the distance grows, and when that light finally arrives, the place it came from is now much farther away than the simple travel time would suggest. That single idea, that space stretches, rather than things merely moving through it, is the key that unlocks everything else tonight. It's why the two maps don't match. It's why galaxies can flee faster than light without breaking any law. It's why some of them are already lost while their old light still pours in. It's the loophole, and the ghost, and the horizon, all growing from the same quiet root. And we're going to sit with that idea, slowly and warmly, in just a little while. But not yet. Right now, there's nothing you need to reach for, nothing you need to chase. 94% of the sky is already beyond us, and there is nothing at all we can do about it, and that turns out to be one of the most peaceful facts I know. There is no missing it. There is no catching it. There is nothing lost through any fault of ours, no train we failed to catch, no letter we forgot to send. It was gone before we arrived, which means the only thing left to do with all that far, unreachable light is to look at it and love it and let it be beautiful. So keep the shape of the two maps somewhere soft in your mind. The wide, wide map of everything we can see, 46.5 billion light-years in every direction, 93 billion across, more galaxies than anyone can count. And the small, quiet map of everything we could ever go to, barely 16 billion light-years, a handful of them bright enough to see, all of them held close by gravity, none of them ever leaving. We can see almost everything. We can reach almost nothing. And somehow, lying here in the dark, that begins to feel less like a loss and more like a kind of grace. Stay with me. We've only just begun to drift, and the strangest, gentlest parts are still ahead, the loophole Einstein allows, the ghosts still glowing in the deep-field photographs, the long, slow story of how space learned to run away from itself. There's no hurry to get there. The galaxies aren't going anywhere tonight. Well, they are, of course. That's the whole point. But they're going so slowly and so gently that we have all the time in the world to watch them leave. And so, softly, let's go back to the very beginning of how any of this came to be known, back to the idea that space itself can stretch, and what happens to the light and to us when it does. But before we do, let me say a quiet word, because it feels like the right place for it. Welcome to the Sleepy Scholar. If you're new here, this is what we do. We take one enormous, beautiful idea, and we walk through it slowly, in the dark, until it stops feeling frightening and starts feeling like a friend. And if you've been here before, curled up under the same blanket on another night, thank you. Truly, it means more than you know. So while everything is still and the lamp is low, if you're enjoying this slow drift through the sky, a gentle like and a quiet subscribe would help more than I can say. Small creators like me really do rely on it. It's the little push that keeps these long, soft nights coming. No pressure at all. Just, if the mood takes you, a tap in the dark. And tell me, while you're there, where in the world are you listening from tonight? What time is it in your corner of the sky? I always love to imagine all of you scattered across the turning earth, each under a different patch of the same impossible universe. Now, settle back down. Let your shoulders sink into whatever's holding you. There's absolutely no need to follow every number, no need to hold the whole thing in your head at once. If you drift off before we reach the end, that's perfectly fine. The galaxies will still be here, and so will I, and the ideas will keep quietly glowing, whether you're awake for them or not. We're going to take this as slowly as falling snow, one small mystery at a time, and no faster. Because here's the thing I want you to carry with you as we go. When you picture the universe, you probably picture one map, one great sphere of stars and galaxies, and somewhere near the middle, a small blue world with you on it, warm under the covers. But there are really two maps laid over each other, and almost no one is ever told about the second one. The first map is the map of everything we can see. Astronomers call its edge the particle horizon, which is just a serious name for the farthest place any light has had time to reach us from. And that edge sits about 46.5 billion light-years away, in every direction you could point. 93 billion light-years from one side to the other. It's a number so large it stops meaning anything, so don't try to feel its size. Just know this, it's a vast, generous map, crowded with galaxies, more of them than there are grains of sand on every beach on Earth. This is the map of what the universe will show you. And then, laid quietly on top of it, there's the second map. The map of everywhere we could ever actually go. Not tonight, Not with our little rockets, I mean the absolute best we could ever do. If we left this very moment and travelled at the speed of light itself, the fastest anything is allowed to move. Even then, there's a wall. Astronomers call it the cosmological event horizon, and it sits at barely 16 billion light-years. That's the whole of it. That's the edge of everywhere we could ever arrive. Sit with those two numbers for a moment, side by side in the dark. 46.5 and 16. The map of what we can see is nearly 3 times wider than the map of where we can go. And because a sphere grows so fast as it widens, the room inside it climbing with the cube of its reach. That gap in the numbers becomes an almost unbelievable gap in the galaxies. When you do the quiet arithmetic, you find that the great glittering majority of everything out there sits inside the map we can see, but outside the map we can reach. Somewhere around 94 out of every 100 galaxies. Already, tonight, forever, beyond us. And I promise we'll get to the how and the why of all of it, slowly, gently, in its own time. I'll show you the exact moment a galaxy's door swings shut, and there's a number for that too. I'll show you the loophole, the reason galaxies can rush away faster than light and yet break no law that Einstein ever wrote, so please don't worry about that just yet. It undoes itself beautifully. I'll show you the ghosts, the galaxies still glowing warmly in our deepest photographs, whose light we can catch, but whose company we've already lost. And I'll show you the strange, lonely far future, when someone will look up and see a single galaxy in an empty sky and believe, wrongly, that theirs is the whole of creation. All of that is still ahead. There's no rush at all. But tonight, before any of the strangeness, I want to give you something to hold, something close and warm. Because in all this talk of what we've lost, it's easy to forget how much is still ours, and it turns out that the little handful of galaxies we could ever reach are the very ones you can walk outside and see with nothing but your own 2 eyes. If you go out under a truly dark sky, away from the city glow, and you know just where to look, you can find a faint smudge of light in the constellation Andromeda. That smudge is a whole galaxy. Andromeda, catalogue name M31, about 2.5 million light-years away, the farthest thing the naked human eye can see. 2.5 million years those photons travelled, only to land in you, quietly tonight, and if the sky is dark enough and your eyes are patient enough, there's a second, dimmer smudge nearby, in the constellation Triangulum. That one's called M33, the Triangulum galaxy, a little farther still, somewhere between 2 and 3 million light-years off. And if you happen to be lying beneath a southern sky, in Chile, or Australia, or the far south of the world, you have 2 more. 2 soft glowing clouds that look almost like torn-off pieces of the Milky Way itself. They're called the Large and the Small Magellanic Clouds, small companion galaxies wheeling around our own, one about 160,000 light-years away, the other around 200,000. And here is the tender little secret hidden inside all of it. Every single one of those galaxies, Andromeda, Triangulum, both Magellanic Clouds, belongs to the same small neighbourhood we do. A gravitationally bound cluster called the local group, which means the only galaxies you can ever point to with your bare eyes are the very ones we could still, someday, reach, but the rest of the sky, the part that needs a telescope, the part that fills the Hubble ultra-deep field photographs and the new images from the James Webb Space Telescope, the part where you find not a handful of galaxies, but hundreds of billions of them, shining across distances that make 2.5 million light-years seem like a walk to the end of the street, All of that is on the other map, the unreachable one. And to understand why, we have to go back, way back, to a question that seems simple at first and turns out to be one of the strangest questions anyone has ever asked about the night sky. Why do the distant galaxies keep moving away from us at all? It sounds like it should have a straightforward answer. Things recede because they're moving. A train pulls away from the station, and the reason is obvious. It has an engine and a direction, and the rails are pointing away. So surely the galaxies are just moving away from us, through space, like trains or rockets or anything else that moves. And if that were true, the implications would be one thing. But that is not what is happening. And here is where the story gets strange, in a way that is, I think, genuinely wonderful once it settles in. The galaxies are not moving through space. Space itself is growing. Space, the very fabric in which everything sits, is expanding. The distance between us and those far galaxies is not increasing, because they're rushing away from some fixed center. It's increasing because the space between us and them is being stretched, the way you might stretch a piece of soft rubber between your hands and watch two dots painted on it drift apart. Neither dot is moving relative to the rubber. The rubber itself is simply becoming more rubber. This is the thing Edwin Hubble noticed. Back in 1929, working at the Mount Wilson Observatory in California, he had gathered light from dozens of distant galaxies and measured something extraordinary in that light. The light was shifted, stretched in a particular direction. The wavelengths had been pulled longer, nudged toward the red end of the spectrum, a phenomenon called redshift. And crucially, the farther away a galaxy was, the more redshifted its light turned out to be. The more distant, the more stretched. He assembled these measurements into something simple and clean, a relationship between distance and recession speed. Farther galaxies are receding faster. The relationship is linear and proportional, double the distance, double the speed. It's now called the Hubble-Lemaitre law, after Hubble and the Belgian physicist Georges Lemaitre, who had worked out some of the underlying mathematics a couple of years earlier. The mathematical form of it reads as recession velocity equals the Hubble constant times distance, a small equation with enormous consequences. Now, the Hubble constant, this is a number that tells you how fast space is expanding per unit of distance. Its value is measured in kilometers per second per megaparsec. A megaparsec is a unit of cosmic distance, about 3.26 million light-years, and the number itself, this Hubble constant, is somewhere in the range of 67 to 73 kilometers per second per megaparsec. That range might seem oddly wide for something scientists have been measuring for nearly a century. There's a reason the range is as wide as it is. There are actually two ways to measure the Hubble constant, and they disagree with each other in a way that has been bothering physicists for years. The first method looks at the early universe. The Planck satellite, a European Space Agency mission that studied the oldest light in the universe, the cosmic microwave background, the faint afterglow of the Big Bang itself, gives a value of about 67.4 kilometers per second per megaparsec. The second method uses local distance measurements, nearby galaxies, a specific kind of exploding star used as a cosmic ruler, a technique that traces through the observable universe's closer neighborhood. That method, led by Adam Riess and the SOES team, gives a value of about 73. The gap between 67 and 73 doesn't look large on a page, but in cosmological terms it's significant. Physicists call it the Hubble tension. It's an open question, genuinely unsettled, genuinely debated, whether the discrepancy points to a measurement error somewhere or whether it points to something new, something the current model of the universe hasn't yet accounted for. For our purposes tonight, what matters is that the value sits somewhere in that range, and either way, the qualitative picture is the same. Space is expanding. Distant galaxies are being carried away by it. And the farther away a galaxy is, the faster it recedes. So, if the speed of recession grows with distance, there must come a point, some particular distance, where the recession speed equals the speed of light. Some threshold beyond which space is expanding so fast that the distance between us and those far objects is growing at 300,000 kilometers per second. That boundary has a name. It's called the Hubble sphere, and it sits at a radius of roughly 14.4 billion light-years. Out at the edge of the Hubble sphere, galaxies are receding from us at exactly the speed of light. Beyond it, they're receding faster than light. And here, if you're still awake, is the moment where the story asks you to sit with something that is genuinely counterintuitive. Because faster than light sounds like it should be impossible. Everything you've probably heard about Einstein's special relativity says that nothing can travel faster than light. The cosmic speed limit, the hard ceiling. So how can anything recede from us faster than light without breaking the rules? The answer is both precise and quietly beautiful, and it is this: special relativity's speed limit governs motion through space, not the expansion of space itself. Those are two different things. Think of the difference this way. Imagine an ant walking along the surface of a balloon. The ant has a top speed, a limit on how fast it can walk along the rubber. That limit is fixed and real. But if someone is inflating the balloon while the ant walks, the distance between the ant and some other point on the balloon can increase faster than the ant can walk, not because the ant broke any rule, but because the rubber between them is growing. The ant is doing its best. The balloon just doesn't care. Space is the balloon. Galaxies are marks on it. Special relativity's speed limit, the rule that says no object can pass through space faster than light, is the ant's walking speed. Nothing breaks any rule when space itself expands faster than light, because that expansion isn't a thing moving through space. It is space. It's the rubber growing. And so, beyond the Hubble sphere, roughly 14.5 billion light-years out, galaxies are receding from us faster than the speed of light, and Einstein is entirely unbothered. There's no violation, no loophole exploited. It's just geometry, the geometry of a universe in which space itself is a dynamic, growing thing, not a fixed and passive backdrop. Now, here is the place where most explanations stop. And here is the place where, if you stop too, you will have missed the most interesting part. The common version of this story goes like this: galaxies beyond the Hubble sphere recede faster than light, therefore they are unreachable, therefore we can never get to them. It sounds airtight. It feels conclusive. It is wrong. Or rather, it's not wrong exactly. It's incomplete in a way that matters enormously. The Hubble sphere is not the boundary of the reachable universe. It is not the line between what we can reach and what we can't. The true boundary, the cosmological event horizon, sitting at that larger distance of roughly 16 billion light-years, is genuinely the limit. But the Hubble sphere, at 14.4 billion light-years, is something else. And the gap between those two numbers is where something surprising lives. Here is the thing. Even in regions where galaxies are receding faster than light, light can still, under some conditions, make progress toward us. A photon launched from a galaxy beyond the Hubble sphere doesn't immediately give up and stop. It swims upstream. The universe's expansion is carrying it backward in a sense, but the expansion also changes with time. The Hubble sphere is not fixed. As the universe evolves, the Hubble sphere grows. And a photon that starts out in a region of faster-than-light recession can, if conditions permit, eventually find itself in a region where recession has slowed enough for it to make headway because the Hubble sphere has expanded outward past it. So the photon keeps going, slowly gaining perhaps, but gaining. This is the picture that Tamara and Charles Lineweaver laid out in careful detail in a 2004 paper in the publications of the Astronomical Society of Australia. Their paper is probably the best single reference on this topic, and their Figure 1, a diagram showing the different horizons of the universe plotted against each other, is canonical in the field. The reason it matters so much is precisely this point: faster-than-light recession is not, by itself, what seals a galaxy beyond reach. The Hubble sphere is not the horizon. If it were, the boundary of our reachable universe would be smaller than it is. The true boundary, the event horizon, that 16 billion light-year radius, is where the expansion of space has become so persistently fast and is accelerating so relentlessly that not even a photon launched today toward a galaxy at or beyond that distance will ever close the gap. No amount of swimming upstream will help. The finish line recedes permanently, no matter how hard or how long the photon runs. So the Hubble sphere and the event horizon are two different things with two different meanings. The Hubble sphere tells you where recession velocity currently equals the speed of light. The event horizon tells you where no signal you send today can ever arrive. The Hubble sphere is about now, about current recession rates. The event horizon is about the entire future, about the cumulative geometry of the universe across all of time. They are related, but they are not the same line in the sand. Conflating them is the single most common mistake in popular explanations of this topic. And the consequence of conflating them is that you'd calculate a smaller, reachable universe than actually exists, cutting off a couple of billion light-years of potentially reachable space. That gap, the space between the Hubble sphere and the event horizon, is genuinely within the reachable zone, even though today those galaxies recede from us faster than light. Extraordinary, really. The universe turns out to be slightly more generous than its most famous speed limit first appears to suggest. And yet, even with that generosity accounted for, the reachable map is still only 16 billion light-years in radius. The visible map is 46.5. And most of the sky, as we've already said, is already lost. But we'll come back to that. For now, let's breathe for a moment with the distance question itself. Because there is something about distance in this universe that deserves a quiet moment of its own. You've probably heard it said that the universe is 13.8 billion years old. The Planck satellite measured this with exquisite precision by studying the cosmic microwave background, the faint, ancient hum of light left over from the Big Bang, permeating the entire cosmos even now. 13.8 billion years. That is the age of everything. And you might think, so the farthest light we can see is 13.8 billion light-years away. Because if the universe is 13.8 billion years old, light has had 13.8 billion years to travel, and nothing is farther than the distance light can travel in that time. It seems completely logical. It is almost entirely wrong. The light from the farthest galaxies we can observe did indeed leave those galaxies when the universe was young. Some of it left less than 1 billion years after the Big Bang. That light has been travelling for close to 13 billion years, and yes, it has covered a distance that light travels in 13 billion years, roughly speaking. That much is true. But, and here is the subtlety, in all that time, while the light was travelling, the space it was travelling through was expanding. The galaxy that emitted the light didn't stay put while the photons made their journey. It was being carried away by the expansion. By the time those ancient photons finally arrive at us, having spent billions of years crossing a universe that was stretching beneath them the whole time, the galaxy that sent them is not 13 billion light-years away. It is much, much farther. The distance we measure for how long ago the light left, the light travel distance, is not the same as the current actual distance to the source. Those are two separate measurements, and they can differ enormously for the most distant objects. The farthest objects we can observe, whose light has been travelling for nearly 13.8 billion years, are now, right now, in this present moment, roughly 46 billion light-years away. Not 13 billion. 46. The universe is 13.8 billion years old, but its observable radius is 46.5 billion light-years, because space never stopped stretching while the light was in transit. Two different maps of the same cosmos. Two numbers describing the same object. Light travel distance, close to 13 billion years worth. Present distance, 46 billion light-years. Both are true. Both are measurements of real things. But they are measurements of different things, and if you confuse them, the universe becomes a smaller, tidier place than it actually is. This is, in a sense, another version of the same fundamental idea we've been circling all along. The visible and the real don't line up cleanly in a universe where space is not a passive stage. The map you draw from the light you receive is always a map of the past, a map of where things were when the light left, adjusted for the journey. Never a map of where things are right now. Never a photograph of the present. Every image we have of the distant universe is a kind of archaeology. The deeper you look, the older the light. The Hubble Ultra Deep Field, that extraordinary photograph taken by the Hubble Space Telescope, shows galaxies formed only a few 100 million years after the Big Bang. Their light has been travelling for over 13 billion years. But those galaxies are not sitting quietly at the edge of a 13 billion light-year sphere, waiting to be visited. They are far, far beyond the reach of anything we could ever send. Their present position, if they still exist at all in recognizable form, is somewhere north of 40 billion light-years away, deep in the unreachable zone. The universe is enormous in ways that resist all ordinary intuition. It is a place where two simple measurements of the same object, how long its light travelled, and how far away it currently sits, give you numbers that differ by a factor of 3. It is a place where the farthest thing you can see and the farthest thing you can reach are not the same farthest thing at all. It is a place where space itself is the variable, the actor, the entity that changes everything. And it is still the only home we have. Settle in for a moment. There's no rush. If you're still awake, that's fine. If you're drifting, that's fine too. These ideas will still be here when you surface. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here is where the story gets strange in a new way. We've talked about expansion. We've talked about recession. We've drawn the two maps, the observable universe and the reachable universe, and noted that the gap between them is vast. 46.5 billion light-years on one side, 16 billion on the other. We've corrected the most common mistake, the one that confuses the Hubble sphere with the event horizon, and showed that superluminal recession alone does not seal a galaxy off from us. It's only the persistent acceleration of space's expansion that creates a true permanent boundary. And that last part, the acceleration, is the heart of it. Because here is the thing, the event horizon, that true reachability limit at 16 billion light-years, does not have to exist. In another kind of universe, with a different kind of expansion history, it simply wouldn't. Every galaxy in the sky could, in principle, eventually be reachable. The reason we live in a universe with a permanent horizon at all is a single, strange ingredient. And that ingredient was only discovered in 1998. We'll come to it properly in a moment, because it deserves its own space, its own slow, careful introduction. For now, just hold this question gently. What if the expansion of the universe weren't accelerating? What if space were expanding, yes, but slowing down over time, decelerating, the way you'd expect if all the gravity of all the matter in the universe were gradually applying the brakes? In that case, things would be different, profoundly different. If expansion decelerates, then the Hubble constant decreases over time. Recession velocities fall. The Hubble sphere grows without bound, eventually encompassing everything. Any photon launched today toward a distant galaxy would find the expansion rate ahead of it weakening, the current pushing against it softening, and eventually it would gain ground. Given enough time, even light from a galaxy currently receding faster than light speed could eventually reach us. Or we could reach it. Horizons would exist in a decelerating universe. Too, there's a particle horizon, the boundary of what light has had time to reach since the Big Bang. But there would be no cosmological event horizon of the kind we're describing. No sealed permanent division between the reachable and the permanently lost. Every galaxy in the observable universe would, on an infinite enough time horizon, fall within reach. But we do not live in that universe. We live in this one, where the expansion is not slowing, where since 1998 we have known with extraordinary certainty that the expansion of the universe is speeding up, accelerating. Space is stretching faster now than it was 1 billion years ago, and it will stretch faster still 1 billion years from now. Something is pushing outward, relentlessly, overcoming the gravitational pull of all the matter in the cosmos. Something with no agreed-upon explanation, no understood mechanism, no name more illuminating than the name we gave it out of near complete ignorance. We call it dark energy. And it is the reason the sky is mostly lost. There's something almost narrative about that discovery, the fact that the universe's permanent horizon, the mechanism behind the unreachable 94%, traces to a thing found only in the last few decades of human history. For almost all of our time on Earth, we didn't know. We thought, or we might have assumed, that the expansion was slowing, that gravity was winning, that eventually, perhaps, the universe would recollapse, the big crunch, the long reversal, everything coming back together the way a thrown ball eventually falls. Or at the very least, that expansion was coasting, running on its initial momentum, gradually breaking. What we found instead was the opposite. The universe is not breaking, it is pressing the accelerator. And the consequence of that, slow, vast, geometric, is that the boundary of the reachable universe is not a temporary condition. It is a permanent one. The horizon is not a wall that will eventually fade as expansion slows and the universe gives us more room. The horizon is a wall that will draw closer over time as acceleration continues and the reachable volume of space shrinks. We are not getting more of the cosmos. We are getting less. That's not how tonight's part of the story ends, but it's where we're headed, and we'll arrive there gently in the parts still to come. For now, it's enough to hold this much. The gap between the visible universe and the reachable universe exists because of acceleration. Without acceleration, there would be no gap. The reason more than 9 in 10 galaxies in the sky are permanently beyond reach is not just expansion, it is accelerating expansion. And accelerating expansion has a cause. A strange, invisible, still not understood cause that makes up roughly 68% of everything in the cosmos. But again, that's for the next stretch of the journey. For now, just rest with the shape of it. The two maps. The stretching fabric. The Hubble sphere at 14.5 billion light-years, where recession currently equals the speed of light, not the edge of the reachable. Just a particular threshold on the way. The event horizon at 16 billion light-years, the true boundary, where no signal launched today will ever arrive. The present distance to the oldest light, 46 billion light-years, not 13.8, because space expanded while the photons were in transit. And the night sky full of galaxies, most of them already beyond reach, still sending their ancient light to our eyes across distances that the word vast cannot begin to hold. The light still comes. The door is already closed. Those two things are both true, and they are not a contradiction. They are just the nature of a universe that has been alive for 13.8 billion years, and that expands as it lives. We receive the messages, we simply cannot reply. Outside your window right now, if there's a window, there are photons arriving from places that no human being, no spacecraft launched on any timetable we can imagine, carrying any technology we can conceive, could ever physically reach. They are crossing your threshold tonight, those photons, after journeys so long that the very fabric of space stretched and grew beneath them for billions of years. They are landing quietly on rooftops and treetops and whatever stretch of sky you have. And most of what they carry comes from the unreachable half of the cosmos. More than the unreachable half, from the unreachable 19/20ths. Which is, I think, one of the stranger things a person can sit quietly with at bedtime. Not frightening, not lonely, exactly, just vast and honest. The universe does not owe us a reachable sky, it gives us a visible one. It lets us see almost everything and touch almost nothing. And in the difference between those two verbs, see and touch, is something that feels almost like a philosophical statement, if you're in the mood for one late at night. We are observers. Extraordinary, improbable, briefly existing observers, sitting in one small bound pocket of a mostly unreachable cosmos, collecting light from billions of years of cosmic history. We can't go most of it. We can see almost all of it. Whether that is consolation or irony probably depends on your mood, your hour, and whether you've already turned off the lamp. If you haven't, go ahead. It'll be fine. The ideas sit just as comfortably in the dark. There's more to come. Why the horizon exists at all, what dark energy actually is and isn't. What it means that we're already receiving light from galaxies we've lost, and what the sky will look like to whatever minds exist, if any do, 100 billion years from now. We'll move through all of it slowly, one small mystery at a time. So let's begin with the simplest question. the one that feels obvious until you actually try to answer it. Why are those galaxies moving away in the first place? And here's the thing. They aren't, quite. Not in the way you might picture it. Not like a ball thrown outward from a central point. Not like debris drifting away from an explosion in the middle of a room. The galaxies themselves are mostly sitting still, in the same way that raisins in a rising loaf of bread are mostly sitting still. What's moving is the bread. The space between things, the fabric, if you want to call it that, is expanding, stretching, and everything embedded in it gets carried along. This sounds like a distinction without a difference, but it matters enormously. And we'll come back to why. The relationship was worked out, or at least first published clearly, by Edwin Hubble in 1929. He'd been measuring the speeds of distant galaxies using something called redshift, which we'll come to in a moment, and he noticed a pattern. The farther a galaxy was from us, the faster it appeared to be receding. Not randomly faster, proportionally faster. Double the distance, roughly double the recession speed. There was a number hiding in that relationship, a ratio, and that number now carries his name, the Hubble constant. We write it h, and it tells us how fast the universe is expanding, specifically how many kilometers per second a galaxy recedes for every megaparsec of distance between us and it. A megaparsec is about 3.26 million light-years, which is already a number so large it's difficult to hold in your head late at night. So let's just say it's a very long way. The current measured value of h is somewhere between 67 and 73 kilometers per second per megaparsec, depending on how you measure it. And the fact that those two numbers disagree, that's not a rounding error. That's an open argument in cosmology right now, a genuine tension between two extremely careful measurement methods that produce slightly different answers. The early universe method uses the Planck satellite, which mapped the ancient afterglow of the Big Bang, the cosmic microwave background, and works backward to get a value of roughly 67.4. The local method uses a chain of cosmic distance markers, calibrated step by step from nearby stars out to distant supernovae, and the team led by Adam Riess at ES gets a value closer to 73. Both are done by serious people using sound methods. Both keep getting more precise. And they still disagree. This is called the Hubble tension, and it's one of the most discussed open problems in contemporary cosmology. It may mean there's new physics we haven't found yet. It may mean something subtle in one of the measurement chains is off by just enough to matter. Nobody knows, which is the kind of honest answer that feels right to sit with quietly before sleep. Either way, 67 or 73, the expansion is happening, and it has a consequence that takes a moment to accept. There is a distance, something called the Hubble sphere, which sits at roughly 14.4 billion light-years from us in all directions. It's not a wall. You wouldn't notice anything special if you crossed it. But it marks the boundary at which galaxies are right now receding from us at exactly the speed of light. One Hubble sphere radius away, recession velocity equals c. Beyond that, recession velocity greater than c. And this is where many people stop and say, wait, that can't be right. Einstein said nothing travels faster than light. He did, and he was right about that. But the limit is on motion through space, not on the stretching of space itself. Special relativity is a local rule. It governs how things move past one another in the same neighborhood. It says nothing about 2 points carried apart, because the space between them is growing. There is no local observer at a distant galaxy watching our Milky Way zoom past at superluminal speed. Locally, everything is fine. The recession velocity that exceeds light is a global coordinate effect, not a local one. Einstein allows it, not as a loophole really, but because it's a different thing entirely than what his limit was describing. So distant galaxies recede faster than light, legally, quietly, and nothing explodes. Now here's where it gets subtle. Here's the piece that most explainers get wrong, and I want to make sure we get it right. Because the error leads you to a false conclusion about what the universe can and cannot offer. You might assume that if a galaxy is receding faster than light, then any signal we send toward it, any light, any probe, anything, could never catch up. And therefore, galaxies beyond the Hubble sphere are already unreachable. That turns out to be incorrect. Photons are patient. And the universe is not a fixed obstacle course. A photon we launch toward a galaxy currently receding faster than light doesn't have to run the whole race at once. It enters space that is in that moment retreating, but the Hubble sphere is not a fixed wall. It's defined by the current expansion rate relative to distance, and as the universe evolves, the photon can find itself, eventually, in a region where the recession has slowed enough relative to the local expansion that it can make headway. Photons can, under the right conditions, swim upstream. They can enter the superluminal zone and still, over billions of years, crawl forward and eventually arrive. This is not speculation. It follows directly from the equations, and Davis and Lineweaver laid it out clearly in 2004, with a diagram that shows exactly which photons make it and which do not. The true boundary, the one that actually divides reachable from not, is not the Hubble sphere. It's something called the cosmological event horizon, and it sits further out at roughly 16 billion light-years in comoving terms. That's the real line. That's the door. And there's a reason the door exists at all. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. Now, back to the door. To understand why a horizon exists in this universe, and why it's permanent rather than temporary, we need to talk about what's doing the pushing. And then we need to hold two ideas at once. One about the age of what we're seeing, and one about where the thing we're seeing actually is right now. Because those are not the same number. Not even close. The universe is 13.8 billion years old. That's what the Planck satellite's measurements of the cosmic microwave background tell us, with remarkable precision. And so you might naturally assume that the farthest things we can see are 13.8 billion light-years away. The light has had that long to reach us. 13.8 billion years at light speed, 13.8 billion light-years. But that would only be true if space had stayed still while the light travelled. It didn't. The light left its source, whatever ancient early universe structure emitted it, when the universe was very young and very small and very different. And then, while the light was in transit, space kept expanding. The source kept receding. By the time the photon arrives here, the object that sent it is not where it was when it sent the light. It's much, much farther away. The light has arrived from a place that has since moved on. The most distant sources we can detect, sitting right at the edge of what's called the particle horizon, emitted their light when they were only a few tens of millions of light-years away. That light has travelled for 13.8 billion years to reach us, but the source itself has in all that time been carried outward by expansion. Its present distance, where it sits right now, in the universe as it exists tonight, is something like 46 billion light-years. We are receiving 13.8 billion-year-old messages from places that are, today, 46 billion light-years away. And that gap, the gap between the age of the universe and the size of the observable universe, is itself a kind of proof. A proof that space has been busy, that while light has been travelling, the container it was travelling through has been stretching, quietly and continuously, in every direction at once. But here is the question we haven't asked yet, and it's the important one. Why does any of this produce a permanent boundary? Think about what we've established so far. Space expands, galaxies recede. Beyond the Hubble sphere, that recession outpaces light itself. But we also said, and this is the part that surprises most people, that faster-than-light recession doesn't, on its own, make a galaxy unreachable. The event horizon is what makes a galaxy unreachable, and the event horizon sits farther out than the Hubble sphere. So the question is, what puts that horizon there? What is it that freezes the boundary and makes it permanent? The answer is dark energy. And to really feel the weight of that answer, it helps to imagine the alternative first. Imagine a universe without it. In a universe where expansion is slowing down, where gravity gradually wins, where the pace of separation between galaxies is decelerating over time, the cosmological event horizon doesn't stay fixed. It grows. It expands outward, year by year, pulling more and more of the cosmos into the reachable set. A photon we launch toward a distant galaxy today might find the going hard at first, might feel like it's barely gaining, but as the galaxy's recession slows, the photon eventually catches up. Given enough time, even galaxies that are currently flying away from us would eventually be within reach. The horizon would keep retreating ahead of us, always promising more. In that kind of universe, a decelerating universe, there is no permanent sealed boundary. There is only more and more of the cosmos waiting to be reached, eventually, by a civilization patient enough and fast enough. Given infinite time and a decelerating universe, you could, at least in principle, visit everything. That is not the universe we live in. We live in a universe where expansion is not slowing down. It is speeding up. The galaxies are not gradually coming to rest, they are accelerating away from us. The space between us and them is not settling, it is stretching faster every year. And in that kind of universe, an accelerating universe, the event horizon does not grow to accommodate us. It shrinks. Slowly, but irreversibly. Galaxies that are currently just inside the reachable zone will eventually drift out of it, and galaxies that are already outside will never come back in. The sealed catalogue gets a little thinner every day. This is the thing that dark energy does to the cosmos, not just expand it, accelerate it, lock the door. And we only found out about dark energy in 1998, which is surprisingly recent when you think about it. For most of human history, and for most of the history of modern cosmology, the working assumption was that the universe was decelerating, that gravity was winning, slowly but steadily. That made intuitive sense. The Big Bang threw everything apart, gravity pulls it back together. So the expansion should be slowing. The only question was whether it would slow to a stop and reverse, the big crunch, or slow asymptotically and continue forever, but at an ever-decreasing pace. Both of those options implied a universe with a gentler fate, a more navigable future. Then came 1998. There were two teams working on this question. Both were doing something very particular. They were measuring the brightness of a specific kind of exploding star called a Type I supernova. Type I supernovae are useful for cosmology in a very precise way. They all explode with roughly the same intrinsic brightness. They're triggered by the same physical mechanism, a white dwarf star accumulating mass until it crosses a critical threshold and detonates. Because they all have roughly the same true brightness, you can use them as cosmic measuring sticks. You observe one, you measure how bright it appears to you, and because you know how bright it actually is, you can calculate exactly how far away it must be. The fainter it appears, the farther it is. Straightforward enough. And if you know the distance and you measure the redshift, how much the light has stretched en route to you, you can calculate how fast the universe was expanding when that supernova went off. Do this for enough supernovae at different distances, different cosmic epochs, and you build a picture of how expansion has changed over time. Is it slowing? Is it constant? Is it speeding up? The first team was called the Supernova Cosmology Project, led by Saul Perlmutter. The second team was the High Z Supernova Search Team, led by Schmidt, with Adam Riess as a key contributor. They were, in some sense, competitors, racing to answer the same question, and both expected to find the same thing. Deceleration. Gravity winning. The universe slowly winding down. What they found instead stopped them cold. The distant supernovae were too faint. Not a little too faint. Meaningfully, persistently, reproducibly too faint. Which meant they were farther away than they should have been, given the redshift. Which meant that in the cosmic epoch, when those supernovae exploded, space had expanded more than gravity alone models predicted. The universe wasn't slowing. It was stretching faster than it had been before. Both teams, working independently, looking at different supernovae with different instruments, arrived at the same conclusion. The expansion of the universe is accelerating. Saul Perlmutter, Schmidt, and Adam Riess received the Nobel Prize in Physics for this in 2011. 13 years after the discovery itself, and the committee's deliberateness was, in part, a reflection of how extraordinary the claim was. You don't rush a prize for finding that everything you thought you knew about the universe's fate was wrong. The cause of that acceleration was labelled dark energy. And we have to be honest about what that name does and doesn't tell us. It doesn't tell us what dark energy is. It tells us what it does. It acts like a property of space itself, a kind of intrinsic energy that drives space to expand, an outward pressure built into the fabric of the cosmos. In Einstein's equations, it appears as something called the cosmological constant, a term he actually introduced, then removed, which came roaring back when the observational evidence demanded it. The mathematics works. The observations match. But what dark energy actually is, at a fundamental level, remains one of the deepest open questions in all of physics. What we do know is roughly how much of the universe it accounts for. When cosmologists look at all the energy content of the observable universe, everything in it counted up. Dark energy appears to constitute approximately 68% of the total. 68% of everything, and we don't know what it is. The next largest share is dark matter, at roughly 27%. Also not directly observed. Also inferred from its gravitational effects, the way galaxies rotate, the way light bends around galaxy clusters, the way structures form in the early universe. Real, certainly, in the sense that something is doing what dark matter is supposed to do. but not directly seen, not yet understood at the particle level. And ordinary matter, the stuff you are made of, the stars, the planets, the gas, the dust, every atom that has ever been named and counted and put in the periodic table, accounts for roughly 5%. 5% of everything. The table of elements that took centuries to build, the entire chemistry of life and rock and fire and sea, is a slim minority. The universe is overwhelmingly made of things we have not yet figured out. But let's stay with dark energy and what it means for the horizon. Because here is the quiet consequence that follows from that 68%. If dark energy is real, if it's responsible for the accelerating expansion, then the expansion will not slow. It will continue. It will, if dark energy behaves as we currently measure it, accelerate indefinitely. And that means the cosmological event horizon is not a temporary condition, it is a permanent one. The line dividing the reachable from the unreachable is not going to dissolve as the cosmos ages. If anything, it will tighten. Every galaxy now just inside the boundary will eventually cross it. No galaxy outside will ever cross back in. The catalogue is not just sealed, it is shrinking. And this is where the story gets strange, in a particular, quiet way. Because while the boundary exists, while the catalogue is sealed, the light doesn't stop coming. Think about what it means for a galaxy to cross the event horizon. It doesn't mean the galaxy vanishes. It doesn't mean a curtain drops, or a screen goes dark, or a signal abruptly cuts. The event horizon is not a wall. It's a threshold of causality, a line past which a signal we send today, travelling at the speed of light, can never catch the galaxy up. It means that if we wanted to affect that galaxy, to interact with it, to send a probe or a message, there is no path through space that would accomplish it. The galaxy has become causally sealed from us, in the forward direction. But light that is already on its way, light that left the galaxy millions or billions of years ago, is still travelling toward us. It's already in transit. It doesn't know about the event horizon. It's just a photon doing what photons do, moving through space, carrying information about the moment it was emitted, and it will arrive here, eventually, as if nothing has changed. So we keep watching. We keep watching galaxies that we've already lost. The light comes in, steady and continuous, redder and dimmer with each passing eon, carrying news of a past we've been permanently severed from. We see them. We can point to them, photograph them, measure their spectra, count their stars. And none of that seeing is the same as reaching. We're watching a farewell that was recorded before we were born, playing back on the only screen available, the night sky itself. It's a little like receiving letters from someone who has already gone somewhere you can never follow. The letters are real, the handwriting is real, the words are full of something true, but the person who wrote them is now and forever somewhere beyond any road you could take. The light still arrives, and it will continue to arrive for a long time, but not forever. And here is the other quiet strangeness. When a galaxy finally fades from view, it does not blink out. It reddens. As a galaxy recedes, and as the expansion of space continues to stretch the wavelengths of its light, that light shifts toward the red end of the spectrum. First, it's visible. Then it becomes infrared, which you can't see with your eyes, but which instruments can detect. Then far infrared, then microwave, then radio waves, stretching toward wavelengths that are meters long, then kilometers long, then longer still. In principle, the light approaches infinite wavelength asymptotically. It never quite reaches it, but it gets dimmer and dimmer, carrying less and less energy, spread across longer and longer wavelengths. until it's effectively indistinguishable from the background hum of the cosmos. No sudden disappearance, no dramatic last flash, just a slow fade, a reddening, a dying away into the static. If you were patient enough and had sensitive enough instruments, you would watch a galaxy redshift itself into invisibility over billions of years. It would be there, and there, and there, each year a little dimmer, a little redder, a little harder to distinguish from nothing. And then one day, though day is not quite the right word for a timescale like that, it would simply be gone. And you could never be sure, from this end, exactly when the farewell finally arrived. Now, there is a specific number that gives you the threshold, the place in the sky where the door, as best we can measure it, has already closed. It's expressed as a redshift. Redshift, remember, is a measure of how much the light has been stretched on its way to us, how much the universe has expanded since the light was emitted. A redshift of 0 means no stretching, no expansion, the source is right here. A redshift of 1 means the universe has doubled in size since the light was emitted. A redshift of 2 means it's tripled, and so on. The higher the redshift, the farther back in time you're looking, and the farther away, in terms of current distance, the source sits. The threshold for causal disconnection, the redshift past which objects are already sealed off from anything we could send them today, sits at approximately Z equals 1.8. That's the number that comes out of the models when you ask, at what redshift does a galaxy fall beyond the event horizon as it currently sits? Redshift 1.8. An object whose light is that stretched was emitted when the universe was younger than roughly 3.5 to 4 billion years old, when the universe was less than a third of its current age. The light that arrives from those objects tonight left them in a cosmos that barely resembled the one we inhabit, a universe where galaxies were younger and more violent, where stars formed at frantic rates, where structures were still assembling themselves from the wreckage of the Big Bang. And those sources, the ones we observe today at redshift greater than 1.8, are, by our best models, already causally disconnected from us. A signal we send them right now, at the speed of light, can never arrive. The expansion of space will carry them beyond the horizon before our message could close the gap. They are reachable in the sense that their light reaches us. They are unreachable in the sense that matters, we cannot go there, and nothing we send can ever follow. Now think about where redshift 1.8 sits in the actual sky. Think about the things we've pointed our telescopes at. The Hubble Ultra Deep Field, released in 2004, a tiny patch of sky, a sliver of apparent emptiness, and within it nearly 10,000 galaxies packed into a region the size of a grain of sand held at arm's length, galaxies upon galaxies, almost all of them very distant, most of them sitting at redshifts well above 1.8. When Hubble stared into that little window and found all of that, it was looking almost entirely at the unreachable set. The galaxies filling that famous image, the ones that made everyone who saw it fall quiet for a moment, faced with the sheer scale of existence. The overwhelming majority of them are already permanently beyond our reach. They were beyond reach before anyone pointed the telescope. And the James Webb Space Telescope, launched in 2021, has looked even deeper. Its deep field programs, JADES and SEERS among them, have pushed into redshifts of 5, 10, 12, and beyond. Galaxies seen as they were when the universe was only a few 100 million years old. Galaxies whose light has travelled for more than 13 billion years to reach the mirror. The web images are extraordinary things. Infrared cameras revealing structure that human eyes can't register directly, translated into visible color so we can see it, showing galaxies in their early youth. Some of them startlingly well formed for how young the universe was at the time. Every single one of those distant galaxies, every smudge and spiral and compact blot of light in the web-deep fields is on the unreachable side of the line, not by a small margin, by an enormous margin. When you look at the US deep field images and feel that particular kind of overwhelm, that sensation of scale, of distance, of time, you are looking almost exclusively at things you can never reach and nothing you send can ever touch. The image that moves you the most is the map of permanent loss. And that's a strange thing to sit with. Not frightening, exactly, not tragic in the way that word usually means, but strange. Strange in the quiet way the cosmos tends to be strange, when you look at it honestly and let the numbers actually mean something. There's a question that sometimes surfaces here, and it's worth asking out loud, because the answer is clarifying. The question is, does it matter? If we were never going to reach those galaxies anyway, if the practical difficulty of traversing even a few light years is already well beyond anything we've managed, does the cosmological event horizon actually change anything real? And the answer, honestly, is it changes everything about what's possible in principle. There's a difference between something being very hard and something being physically impossible. A mountain is hard to climb. A destination you can never reach, no matter how fast you go or how long you travel, is in a different category. The event horizon is the second kind of limit. It doesn't mean we couldn't climb a very tall mountain. It means the territory on the other side doesn't exist, from our perspective, not as a reachable place. It can only ever be a viewable one. And there's something about that which changes the texture of the night sky. Or at least, it changes the texture of thinking about the night sky. When you look up on a clear night and see the stars, and between the stars, the vast dark that contains those hundreds of billions or trillions of distant galaxies, invisible to your eye but present in the data. You are looking at two very different kinds of things at once. There are the things that are part of your universe, in the full sense, the places that could be reached, that belong to the same causal story as you do, that share a future with you. And there are the things that are only ever views from here, places that have already left the story, already closed their chapters, that will send their light in and never receive anything back. Most of what you're looking at is the second kind. The night sky, in that sense, is mostly a museum, a beautiful, almost inconceivably vast museum of things already beyond contact. The light that arrives from those places is not nothing, it's extraordinary. It carries real information about the physics of those galaxies, the conditions of the early universe, the way structure formed in the first billion years of cosmic time. We learn enormous things from it. The deep field images have rewritten our understanding of how galaxies assemble, how quickly they formed, how early the first stars ignited. None of that learning becomes less valuable because we know the source is beyond reach. But the two facts exist together. The information arrives. The source is gone, in the sense that matters. And every night, without fanfare, the window narrows just a little more. Not because of anything catastrophic, not because of any collision or disruption, simply because acceleration continues and the expansion carries distant galaxies a little farther from us each year, and the light that arrives tonight is a little older than the light that arrived last year, and eventually the oldest light. The most stretched, the most ancient, will redshift itself out of detectability. Not all at once. Quietly, it is worth spending a moment here with what the James Webb Space Telescope has added to this picture. Because Webb is seeing things that were simply inaccessible before it. It's operating in the infrared, which means it can pick up light that has been stretched by expansion from what was originally visible or ultraviolet wavelengths into the infrared range, which is exactly the kind of stretching you get from very high redshift sources. Things that Hubble couldn't see in its optical range, Webb sees. Galaxies at redshifts of 12 or 15, seen as they were when the universe was only 200 or 300 million years old, are not just detectable to Webb, they're detailed. You can see their structures, you can measure their star formation rates, you can see, in some cases, that they are surprisingly massive for how early in cosmic history they appeared. And every one of those early, massive, surprising galaxies is well past the threshold, well past redshift 1.8, already sealed off, already on the far side of the event horizon, already beyond any path we could take. There's something almost meditative about that. The more powerful our telescopes get, the farther we see. And the farther we see, the deeper we look into the unreachable set. The improvement in our instruments doesn't expand the reachable universe, it expands the museum. We build more powerful telescopes, and we see more galaxies we can never visit. That is not a lament exactly. The museum is magnificent. The information it provides is invaluable. But it's a reminder that seeing and reaching are two fundamentally different things. They always were, even before we understood the cosmological event horizon. But now that we understand it, we can say with precision that those two things, visibility and reachability, come apart at a very specific point in the spectrum, at a specific redshift, at a specific threshold that the physics of our universe has written into space itself. Redshift 1.8. A number that divides the sky into a small reachable part and an overwhelmingly large unreachable part. A number that tells you, with remarkable specificity, which of the galaxies you're looking at have already said goodbye and which still belong to the same story you're in. And the ones that belong to your story, the ones on the near side of that line, are something we'll come to next. They are few. They are precious. And some of them you can see tonight without a telescope at all. But before we get there, it's worth letting the scale of what we've just covered settle in gently. We've traced the logic from expansion to acceleration to dark energy to a permanent sealed boundary. We've seen why the horizon exists, not because of any law of motion, but because of the nature of space itself, a property that Einstein's equations allow for, that 1998 observations confirmed, and that two teams of astronomers received a Nobel Prize for discovering. We've seen that the light from the unreachable set keeps arriving, keeps feeding us information, even as the causal connection has already been severed, and that when that light finally fades, it goes gradually, a slow reddening into the cosmic background, not a dramatic exit. We've seen the threshold, redshift 1.8, the place in the spectrum where the door closes. And we've seen that the most celebrated deep sky images in history, the Hubble Ultra Deep Field with its 10,000 galaxies, the JWST deep fields with their startling glimpses of the early universe, are almost entirely composed of galaxies on the wrong side of that threshold. The richest, most visually overwhelming parts of the sky are the parts we've already lost. If you're still awake, and it's perfectly fine if you're not, the ideas will be here when you return. There's one more thread worth following before we come around to the islands of the reachable. And that thread is about what happens to the light as it fades, not to us watching it, but to the light itself. A photon doesn't know where it's going when it leaves a galaxy. It doesn't know whether it will be received, whether the receiver will be able to reach back, whether the universe will have expanded in ways that make the sender forever distant. It just travels. At the speed of light, through whatever space is available, in whatever direction it was emitted. When a galaxy is just crossing the event horizon, when it sits right at the boundary between causally connected and causally sealed, its light is undergoing something interesting. The photons leaving that galaxy in the direction of Earth are still able to make the journey. They'll have a hard time of it. The expansion of space will work against them. Like trying to run towards someone who is walking away from you on an expanding floor. The photons will make progress, slowly, but they'll make it. Eventually they'll arrive. But the photons leaving that same galaxy the year after, and the year after that, will find the geometry slightly less favourable. Each year the expansion has stretched space a little more, and the photons have a slightly harder climb. Eventually, and this is the moment the door closes, the expansion has accelerated enough that even light launched directly toward us from that galaxy cannot close the gap. The floor is expanding faster than the photon can run, and that photon will never arrive. From our perspective, we'll never see it. But we won't see its absence either. We'll just see the last light that made it, increasingly redshifted, increasingly dim, slowing in its apparent fading, approaching invisibility asymptotically. If we're watching that galaxy's spectrum carefully, we'll see the redshift increasing year by year. The light stretching, the energy per photon decreasing, the wavelength lengthening toward the radio and beyond. What we will never see is the moment of disconnection. There's no flash, no marker, no detectable signal that says this is the last photon to make it. The stream just thins, and eventually what's left is indistinguishable from background. The galaxy will have been there, and then it will be effectively gone, and the transition will have been so gradual that no single moment announces it. The universe does not mark its farewells clearly. And that, in a strange way, is consistent with everything else we've found tonight. The two maps, the visible and the reachable, don't announce themselves in the sky. You can't look up and see a line dividing what's yours from what's not. The redshift threshold isn't painted in different colours. The event horizon has no physical marker, no edge, no visible boundary. It's a line that exists in the mathematics, confirmed by observation, defined by the physics of accelerating expansion. But in the actual night sky, everything looks the same. Light comes in from every direction, from sources at every distance, carrying news of every epoch. The sky does not tell you which of its lights come from places already beyond your world. That knowledge required telescopes and patience and mathematical cosmology, and eventually the work of two teams of astronomers in the late 1990s staring at the light curves of exploding stars and finding, in their unexpected faintness, the fingerprint of a cosmos accelerating away from itself. Which means, in a very real sense, that every time you look at the night sky now, with that knowledge somewhere in the back of your mind, you are seeing two things at once: the sky as it appears, and the sky as the physics says it is, divided, most of it already a farewell, a small and precious fraction still yours. And what is that small and precious fraction? What remains on the reachable side of the line? That is where we're going next. To the islands, to the bound things, to the few galaxies you could, in principle, still visit, to Andromeda, falling toward us even now, and to the future it is tumbling toward, and to the remarkable and slightly melancholy fact that the reachable universe is slowly consolidating, the separate islands pulling together into one, while everything else recedes beyond view. There's a kind of peace in what remains actually. The reachable set is small, but it is ours, completely, gravitationally bound, forever, and some of what's in it is remarkable. But that is for a moment from now. For now, let the larger picture settle. Dark energy, 68% of everything, still mysterious at its core, is what draws the line. It's what separates the expanding cosmos into the seen and the unreachable. It's what turned a universe that might have been, in some distant future, fully explorable into one with a fixed and permanent horizon. It's what ensures that the farewell is already recorded, that the light we see tonight from distant galaxies is the final correspondence from places we've already lost. The universe is accelerating. The door was always going to close, and for most of what's in the sky, for roughly 9 out of every 10 galaxies you can detect with even the most powerful instruments, it already has. Somewhere, if you're lying still enough, you might feel that in a particular way. Not as loss, exactly, something quieter. The way you might feel hearing that a place you loved has changed beyond recognition, a neighborhood, a landscape, something from before. The thing is still there, in one sense. The light still comes. But the version of it you could have reached is already past. The night sky holds all of that, the light and the knowing. And there's something about that combination, sight without reach, presence without contact, a correspondence that only runs one way, that feels, if you let it, less like tragedy and more like a very large, very quiet form of wonder. The galaxies keep sending their light. We keep receiving it. And somewhere in the dark between those two facts is the shape of the universe we actually live in. So let's talk about what stays, because there's a version of this story that ends in pure loss, a catalogue of everything we've already given up, everything the horizon has swallowed, and that version is true as far as it goes. But it's not the whole picture, and the part that's missing is in some ways the most quietly extraordinary thing in all of cosmology. There are galaxies we will always be able to reach. Not most of them, not even a comfortable fraction, but some. A small, warm, gravitationally bound family of worlds that expansion cannot touch, cannot carry away, cannot ever separate from us. And they will be with us, with whatever comes after us, not just for a very long time, but for as close to forever as anything in this universe gets. That family has a name. It's called the local group. The local group is the collection of galaxies bound together by their own mutual gravity, a gravitational knot that expansion simply cannot untie. Gravity, at close enough range, is stronger than the slow, patient stretching of space. It holds, and within the local group, that hold is total. These galaxies are not drifting apart. They are not receding. They are staying, and in some cases, they're actually drawing closer. The local group has roughly 80 members. Most of them are small, dwarf galaxies, irregular clumps of stars, modest companions that orbit the larger members, like moons orbit a planet. But the anchors of the group are familiar. The Milky Way, of course. Andromeda, which you might know better as M31, the one smudge of light visible to the naked eye beyond our own galaxy, a faint, elongated glow in the constellation Perseus, when conditions are right and the sky is truly dark. The Triangulum galaxy, M33, slightly smaller, slightly harder to find without optical help. And then the smaller satellites, the Large Magellanic Cloud and the Small Magellanic Cloud, visible from the southern hemisphere, just hanging there in the sky like two detached fragments of the Milky Way itself. Every galaxy in the local group is reachable, every single one. If you could board something moving at the speed of light today, and this is purely a thought experiment, gently offered, you could point it at any member of the local group and eventually arrive. Not quickly. Not in any span of time that means anything to a human life or 1,000 human lives. But arrive. The rest of the sky? The rest of the sky is already leaving. And this is what makes the naked eye sky so quietly remarkable on a clear night. When you step outside and look up and let your eyes adjust, and you find that soft blur of Andromeda, maybe you've seen it before. Maybe this is the first time you've gone looking. You are looking at one of the reachable ones. You are looking at something within the small sealed catalogue of places we have not yet lost. Everything visible to your unaided eye in the galaxy category is inside the local group. The impossible to reach 94%? Those require a telescope. Those are invisible to the naked eye. The galaxies you can point at tonight are the ones you could theoretically go to. And then there's Andromeda itself, which is doing something the others are not. It's coming toward us. At roughly 110 kilometers per second, that's about 250,000 miles per hour if you prefer, Andromeda is falling in our direction. Not because of any special intent, not because we're pulling on it harder than anything else, but simply because that's what gravity does at close range when two massive things sit near each other. It tugs, it draws, and Andromeda and the Milky Way have been tugging on each other since long before any life existed anywhere between them. In approximately 4.5 billion years, give or take, and with some genuine scientific uncertainty about the exact trajectory, because the transverse velocity, the sideways drift, is harder to measure than the direct approach, Andromeda and the Milky Way will collide. Or rather, they'll pass through each other, gravitationally interact, throw stars around, and eventually settle into a single merged system. The stars themselves are so spread out that relatively few of them will physically collide. Space is empty enough that a galaxy merger is less like two solid objects crashing and more like two clouds interpenetrating and slowly, over hundreds of millions of years, combining into one shape. Astronomers have a name for what they expect to emerge from that merger. A nickname, really, they call it Milkomeda. Milkomeda, a galaxy made of two we know, everything from the Milky Way and everything from Andromeda, slowly stirred together by gravity over an almost unimaginable span of time, settling eventually into a single elliptical galaxy that looks nothing like either of its parents. And by that point, by the time Milkomeda has settled into its final shape, which won't happen for tens of billions of years at minimum, the rest of the local group will likely have merged in as well. The Triangulum Galaxy, the Magellanic Clouds, the dozens of dwarf companions, all of them pulled together by the same gravity that already holds them, folded in over time into a single massive object. The reachable universe consolidating itself, as though gathering close while everything else departs. The universe doesn't just separate us from what we can't reach, it also draws together what we can. There's something comforting in that, if you want it. Not just that the reachable set stays, but that over incomprehensible timescales, it knits itself into a closer and closer family. The final state of everything within our gravitational reach is not drift, it's union. But now let's go slightly farther out, not past the horizon, not into the irretrievably lost, just to the edge of where the question gets interesting. About 53 to 65 million light-years away, the measurement range reflects genuine uncertainty in how we pin down the distance, sits the Virgo cluster. The Virgo cluster is large, over 1,300 galaxies, packed into a relatively dense region of space, anchored by a few massive elliptical galaxies at its center. It's the heart of the Virgo supercluster, and by extension a gravitational center for the broader structure that includes, at its outer edges, our own local group. We're part of the same vast architectural context. Not bound, exactly, not the way we're bound to Andromeda, but affiliated in a loose gravitational sense. And yet, the Virgo cluster is receding. Not dramatically, not at some enormous fraction of the speed of light, but measurably, consistently moving away from us as expansion carries it further. Whether it falls cleanly on the reachable or the unreachable side of the line depends, in practice, on the precise value of the Hubble constant and the exact behavior of dark energy, and given what we've already talked about, you'll understand why that's a genuinely uncertain question. But Virgo is close to the boundary. It's the so near, and yet already slipping example, more than 1,000 galaxies, each containing hundreds of billions of stars. At a distance that on cosmic scales feels almost neighborly, and yet the expansion is doing its patient work. Every second that passes, Virgo moves a little farther from reachable. Sit with that for a moment. 1,900 galaxies. Distances we cannot physically picture without abstractions. And still, on the scale of this conversation, Virgo is the near one, the almost within reach one, the galaxy cluster that illustrates the edge. Now multiply outward. There's a question that sometimes comes up in discussions of the observable universe: how many galaxies are there? It's a question that sounds almost childlike in its simplicity. Just count them, right? And yet the answer has changed significantly within living memory and may not be settled yet. For a long time, the standard estimate based on Hubble Space Telescope observations hovered around a few 100 billion galaxies in the observable universe. Then in 2016, Christopher Consolis and his colleagues published an analysis in the Astrophysical Journal suggesting the number was dramatically higher, closer to 2 trillion. 2 million galaxies. The argument was that deep field images, even very deep ones, still miss the faintest, smallest, most distant galaxies, and that accounting for those missed populations pushed the total far above previous estimates. But in 2021, using brightness data from the New Horizons spacecraft, which is now so far from Earth that it has a uniquely dark vantage point away from the solar system's own glow, Todd Lauer and colleagues measured the total brightness of the extragalactic background light and found it lower than 2 trillion galaxies would predict. The revised estimate pointed back toward hundreds of billions, not 2 trillion. The question is still being worked through. 2 trillion might be too high. A few 100 billion might be closer. Either way, the scale is so far beyond ordinary experience that the difference between 2 trillion and 500 billion registers as almost philosophical rather than practical. The reachable fraction is tiny in either case. A small percentage of an enormous number is still an enormous number, in the abstract, but it's a fixed, non-growing catalogue, and it's mostly already gone. Of all those galaxies, however many there are, the ones we could ever physically visit are the ones inside approximately 16 billion light-years. The event horizon boundary. The permanent line, And that volume, as vast as it sounds, contains only a small fraction of what the observable universe holds. The rest of it is still there. In a sense, the light still arrives. But they are gone from us in the only way that ultimately matters for any physical creature. We cannot go to them, and they cannot come to us, and nothing we send will ever bridge the gap. Now, what does all of this look like, eventually? There's a paper by Lawrence Krauss and Robert Scherer, published in 2007 in the journal General Relativity and Gravitation, titled The Return of a Static Universe and the End of Cosmology. It's a remarkable document. Not alarming, nothing in cosmology that happens over trillions of years is alarming in any immediate sense, but genuinely, quietly astonishing in what it describes. Krauss and Scherer worked out what the sky looks like for an observer in the far, far future. Not millions of years from now, not billions, trillions, a time frame so deep that the universe itself is almost unrecognizably different from the one we inhabit tonight. Here's what happens if dark energy continues behaving as it currently seems to behave. Everything outside the local group, everything we haven't already discussed as bound and reachable, recedes past the event horizon. Not all at once, not dramatically, but steadily, inexorably, galaxy by galaxy, cluster by cluster, as the expansion accelerates. The Virgo cluster, the more distant superclusters. Every galaxy in the Hubble ultra-deep field, every object captured in the JWST deep fields, they all slip past the horizon, their light increasingly redshifted, their signals stretching toward infinitely long wavelengths, their images reddening and dimming over billions and eventually trillions of years until they fall below any conceivable instrument's ability to detect. They don't blink out. They fade. Asymptotically, mathematically, their light wavelength stretches toward infinity, and their apparent brightness falls toward zero. It's not a light switch. It's more like a photograph slowly bleaching in the sun. The image lingers for a long time, recognizable for a while, and then there comes a moment when you realize it's mostly gone, and then later another moment when it's fully gone. And in between there was no clear boundary, and when that fading is complete, when every external galaxy has finally crossed the threshold of detectability, a future observer will look up at the sky and see a single galaxy. Just one, the merged product of the local group, Milkomeda, or whatever it has become after further mergers. One large galaxy, surrounded by an apparently empty sky. No other galaxies, no cosmic web, no deep fields full of faint smudges. Nothing, and this is the part that Krauss and Scherer point out with a kind of quiet intellectual vertigo. That future observer, if they exist, will have no way of knowing what we know now. They won't be able to see the cosmic microwave background in any useful way, because it will have redshifted to wavelengths so long they'll be undetectable. They won't be able to measure the expansion of the universe, because there'll be nothing external to measure the expansion against. Every reference point will have vanished. They'll see one galaxy in an apparently static, apparently eternal sky, and they'll have every reasonable scientific justification for concluding that theirs is the whole universe. They'll be wrong, in a deep sense. The universe will still be out there, vast and expanding, full of light we can no longer see. But the evidence for it will have been taken away, not by censorship, not by any deliberate mechanism, just by physics, just by the slow, patient work of acceleration. Krauss and Scherer put it plainly, future cosmologists will lack the information to reconstruct what we take for granted today. The Big Bang, the expansion, the other galaxies, all of it erased from the sky, We live at a privileged moment. A moment when the universe is still young enough, and the galaxies still close enough, and the light still bright enough, that the whole picture is visible to us. That window will not stay open. We can see the whole sky tonight. Somewhere in that thought is something that deserves a moment's stillness. There's one more thing worth saying before we leave the science behind and simply rest in all of this. Everything we've talked about tonight, the event horizon, the 94% already beyond reach, the fading of the far galaxies over trillions of years, the lonely future sky, all of it assumes that dark energy continues behaving the way it currently appears to behave. That it acts like what physicists call a cosmological constant, a fixed, unchanging energy of empty space that pushes outward at the same rate forever. That's the standard model. That's what fits the data best, as of this conversation. But in 2024, early results from a major new survey called DESI, the Dark Energy Spectroscopic Instrument, mapping the three-dimensional positions of tens of millions of galaxies, raised a tentative, unconfirmed, genuinely interesting possibility that dark energy might not be constant, that it might be weakening over time, or changing in character, in ways that don't fit the simplest model. If that's true, and it's a careful if, not a certainty, not even a strong probability yet, then the horizon might not be as permanent as we've described. A weakening dark energy could mean the expansion decelerates, the horizon retreats outward, and galaxies we thought lost become reachable again. The sealed catalogue reopens, the lonely future sky doesn't materialize, we don't know yet. The DESI results need confirmation, more data is coming. This is cosmology at the frontier, genuinely unsettled, genuinely exciting, genuinely alive. What it means for now is that the story we've told tonight is the best current answer, not the final one. The 94% is a robust estimate, not a carved certainty. The event horizon is real given what we know and could shift given what we don't. Science lives in that gap between the current answer and the better one still coming. Hold that lightly. It's one of the most honest things anyone can say about the universe. And now, gently, let the numbers go. Because we've come a long way tonight, we started with a simple thing. A sky full of light. The kind of light you might have seen on a clear night if you've ever been somewhere dark enough, away from the orange glow of a city. A sky where you could actually feel the depth, where it stopped looking like a flat ceiling dotted with points and started feeling like a space you were sitting inside. A volume. Something with dimension and distance. That light is still real. The wonder of it hasn't changed. But now you know something about it that most people don't carry around consciously. That the sky you're looking at is split into two maps that don't line up. The map of what you can see, stretching out 46.5 billion light-years in every direction, a sphere almost inconceivably larger than the 13.8 billion-year age of the universe, because space expanded while the light travelled. And the map of where you could ever go, a smaller sphere, only about 16 billion light-years across, bounded not by how far you could travel but by whether the destination will still be there when you arrive. Those two maps diverge. Significantly. Permanently. About 94% of what the sky contains is in the first map, but not the second. You can see it. You could never reach it. And not because we lack the technology, or because we'd run out of fuel, or because the distance is discouraging. Because the universe itself is accelerating away, and the door to those galaxies closed before any human being drew breath. The light still comes. It will keep coming for billions of years, slowly reddening, slowly dimming. The galaxies are still there, sending their old correspondence into the dark. but the version of them we could have visited is gone. Whatever they are now, and because of the speed of light, we can't know what they are now. We'll never see it. We'll always be receiving the past, and the present will always be out of reach. There's a feeling that comes with really sitting inside that idea. Not fear, exactly. Not grief, quite. Something that takes up more space than those words. Something closer to awe at the scale of it, and maybe something like gratitude too. Gratitude for living in the moment when the full picture is still visible, when the sky is still rich with light from a universe we can actually comprehend the shape of. The galaxies you can see with your naked eye tonight are the reachable ones. Andromeda falling toward us. Triangulum, quiet and faint. The Magellanic Clouds, if you're in the southern half of the world, looking like chips of the Milky Way that broke off and drifted slightly to the side. All of them inside the local group. All of them gravitationally held, all of them yours, in the only sense the word can mean across those distances. And you are part of the same family. You're made of atoms forged in stars that have been part of this local group for billions of years. The carbon in your bones, the oxygen you're breathing right now, the iron running slow circles through your blood, all of it was processed through stellar furnaces that are as bound to this gravitational family as Andromeda is. You're not separate from the reachable universe. You are it. You're one of the things it contains, the thing that can look up and ask the question, the thing that can lie still in the dark and feel the size of everything around it, and somewhere in the atoms of you is the same stuff as Andromeda. Not metaphorically. Literally, we're made of the same interstellar material, processed differently, scattered differently, but continuous across the whole local group in the same way the ocean is continuous from one shore to another. You are not watching the universe from outside. You are inside it, looking up. And what you can see from in here, this temporary window, this privileged moment before the galaxies fade and the sky empties, is something extraordinary. A universe that is simultaneously giving you its light and withholding its distance. Showing you everything, offering you a small fraction. Letting you see galaxies it will never let you touch. There's something deeply, gently human about that situation. The visible and the unreachable. The known and the forever out of reach. We live in it on smaller scales all the time. The places we can see in photographs but will never visit. The lives we can imagine but will never live. The moments that passed before we arrived. The universe is doing the same thing, but on a scale that dwarfs all of our ordinary versions of it. And yet the feeling it produces, when you let it, is not so different. Something like longing, something like wonder. The willingness to sit with a beautiful thing you cannot hold. Earlier, when we started, I asked where you're listening from tonight, and I meant it genuinely. Whether you're lying in a bed somewhere in the northern hemisphere, the window dark, the city quiet outside, or stretched out somewhere under an actual open sky. Stars overhead, and the ground cool beneath you, or maybe somewhere in between, wherever you are, right now, your corner of the cosmos is inside the reachable set. You're inside the gravitationally bound world, the part that holds together, the part that stays. The universe is very large. Most of it is already gone from us, in the only physical sense that matters. But the part you're in, this small, warm, gravitationally knit family of worlds, is not going anywhere. That's a good thing to carry into sleep. If you've enjoyed this slow journey tonight through the strange and the vast, a gentle like or a subscribe if you haven't already really does help this little channel keep going. And I mean that simply and sincerely. Small creators like this, one rely on that support to keep making things. If you want to leave a comment, I'd love to know where you're listening from tonight and what the sky looks like from there, or whether you've already closed your eyes. Close the books, dim the lamp. Class is over, sleepy scholar. And that brings us to the question underneath all of this. Not what we've lost, but what remains. The local group is what astronomers call the small cluster of galaxies the Milky Way calls home. It is not large by the standards of what we've been moving through tonight, nothing like the Virgo cluster or the great filaments that structure the observable universe at its largest scales. The local group is modest. Intimate, even. At its center sit two great spirals, ours, the Milky Way, a barred spiral with perhaps 200 to 400 billion stars arranged in arms that take light 100,000 years to cross. And Andromeda, M31, roughly 2.5 million light-years away, tilted toward us in the sky, so wide in angular extent that on a very dark night it covers a patch of sky 6 times the width of the full moon, though far too dim for most eyes to find against the background glow. Then there is the Triangulum galaxy, M33, a third spiral, somewhat smaller and farther. And around those 3 great anchors orbit perhaps 80 or so satellite galaxies and dwarf systems, the large and small Magellanic Clouds hanging low in the southern hemisphere sky like quiet companions, and smaller ones with quieter names, Sculptor, Fornax, Leo Ice, all of them orbiting, held in place by the mutual gravity of the group. All of it is gravitationally bound. And that distinction matters enormously. Dark energy operates on the vast, mostly empty distances between galaxy clusters and superclusters. It pulls space apart at the scales where galaxies are not tethered to each other, where there is nothing to hold the stretching in check. But it cannot reach inside a system that gravity already holds together. What is bound stays bound. The expansion does not apply within the local group. Its members are not receding from each other. They are not being pulled apart. And that means everything within the local group, Andromeda, Triangulum, the Magellanic Clouds, all 80-odd smaller companions, stays reachable, not just now, permanently, in the only physical sense that word can mean across cosmic time. Andromeda, specifically, is doing something that makes this feel even more tangible. It is not moving away from us, it is falling toward us. Right now, while the room around you sits quiet, Andromeda is approaching at roughly 110 kilometers per second. Not carried outward by the expansion of space, but pulled inward by the gravity tying the local group together. In approximately 4.5 billion years, the two galaxies will begin the long, slow process of merging. Not a violent impact of individual stars, most stars are far too spread out for that, but a mutual disruption across hundreds of millions of years. Each spiral's arms pulled wide, both systems interpenetrating and reforming into something neither is now. Astronomers have already named what emerges from the other side, Milkomeda, one galaxy made from ours and theirs. It is, in a way, one of the most certain things we know will happen to us at a cosmological scale. Amid all the genuinely unsettled questions, the Hubble tension unresolved. Dark energy's nature still unexplained at its root, the eventual merger with Andromeda is among the best measured future events in all of astronomy. It is coming, slowly, beautifully, across a span of time the human mind was not really built to hold. The Virgo cluster sits about 53 to 65 million light-years away, depending on which measurements you use. It is enormous, more than 1,300 galaxies gathered into a single gravitational family, anchored near its heart by M87, the giant elliptical whose central black hole was the first ever directly imaged, a shadow the size of our solar system cast against the glow of infalling matter. Lineweaver, the supercluster of which we are a part, is in some sense falling toward Virgo even now, drawn by its mass the way rivers fall toward the sea. And yet Virgo is not gravitationally bound to us. It sits at the uncertain frontier of the reachable map, so near by cosmic standards, and yet depending on the precise behavior of dark energy, perhaps already on the wrong side of the line. 1,000 galaxies, close enough to name, close enough to photograph in detail. Already, perhaps, slipping past the frontier. One number before we go, worth pausing over for just a moment. The total count of galaxies in the observable universe has been revised more than once. A 2016 study by Christopher Consolis and his team, using Hubble Deep Field data and careful models of how galaxies fade and merge across cosmic time, argued for roughly 2 trillion, a figure that struck many as startling, far higher than the 100 billion estimate that had been in common use. Then in 2021, a team led by Todd Lauer used data from the New Horizons spacecraft, which had travelled far enough from the Sun to measure the faint optical glow of deep space without the scattered light of the inner solar system interfering, and arrived at a lower number, still hundreds of billions, but not 2 trillion. The conversation is ongoing. The tools are still improving. Either way, hundreds of billions or 2 trillion, the fraction of all of that which is reachable, is the same small thing. The reachable catalogue is sealed. Galaxies leave it, and none return. Lawrence Krauss and Robert Scherer traced the long future carefully in a 2007 paper. In 100 billion years or more, long after the stars of this era have mostly burned out, long after the local group has consolidated through its mergers into a single quiet remnant, everything beyond that remnant will have receded past the event horizon. The light from every other galaxy will have stretched to wavelengths too long to detect. The cosmic microwave background, which today gives us a direct window onto the universe's earliest moments, will have faded past any threshold any instrument could reach. Whatever minds exist then will look up and see one galaxy in an apparently empty sky. No recession, no expansion, no fossil of the Big Bang. They may conclude, with every tool they have, that the universe is static and eternal and alone. They will be wrong, but they will have no way to know it. We live in the brief era when the evidence is still legible, when the universe is still telling its own story, and we have not yet lost the means to listen. One honest note before the quiet settles completely. Everything said tonight about reachability assumes dark energy is constant, a steady, unchanging pressure across all of cosmic time, the way it appears when we measure it today. The 2024 results from the DESI survey, which mapped the large-scale structure of the universe with new precision, raised a genuine and not yet settled question. Dark energy may be evolving, perhaps slowly weakening. If it is, the boundary of the reachable set changes. Some of what we have called permanently lost might not be. The map might need revising. It is held, as good science holds all open questions honestly, without forcing an answer the data hasn't yet given. The universe does not owe us clean lines, and the feeling all of this produces, when you let it settle without pressing too hard against it, is not only loss, there is something else alongside it. Something like gratitude for being here now, when the sky is still full, when there is still light to read, when the story is still unfolding. The far galaxies, the unreachable ones, the ones we are even now watching fade toward infinite redshift, were not without purpose. Their gravity shaped the cosmic web that gathered our supercluster into being. Their light travelled through the expanding dark across billions of years and reached here, reached you. They sent what they could send, across all that distance, long be.